Hello and welcome. In the next video, he'll be building our first generative adversarial network to learn MNIST dataset. And we'll start with just looking at the results of one of the networks I've just trained. In a moment, we'll actually train our network for quite some time, and then I will explain the code behind it. So this is the result of training a GAN that I did. It's actually located in the source directory in, I think it's in results origin, something like that. And this is the absolutely first image, and we have in our MNIST dataset, we have handwritten numbers. So at the beginning, when we just inject into generator the noise, we'll get this kind of results. And you can see it's nothing really that interesting. But as we go along, we can see that slowly we can see that some of the digits, they start appearing, they start to get shape. And this was actually trained for 50 epochs with the current setup that the training script has, and it took around 2 hours or so, maybe a little bit more with just CPU. So this is quite a nice results for this short of time and only for CPU. So as we go along, you can see that we can see more and more digits appearing there, and this is our goal. This is how generator is actually learning to create those digits that are similar to the one that we have in MNIST dataset. So keep in mind that this is quite amazing, because we are, as an input, our generator has only noise, which is just pretty much random values, and it actually learned quite a bit. So as we progress, and we can see more and more digits that looks actually like digits. Yeah. And when we go till the end, we can see that, the results is pretty good for such a short amount of time, also for CPU only. So if you want to get started with training your own GAN, you can just go to the source directory for this section and type in python 3 train.py and hit enter. And this script will show you which stage is it in. So by default, it's set up to train for 50 epochs or for 50 training sessions, and it's enough to create those kind of results that you've just seen. And the script is set up in a way that you should be able to reproduce the exact same results. So we'll leave this to work for a while, and we'll examine the results of that in a moment. And before we get into that, one thing to keep in mind: this script will save its output, the one that we've seen just a minute or so before. It will save it in a results directory, in a source directory for this section, and will do that every even number of epoch, right? So it will start with just epoch 1, and it will save the output of the generator for epoch 1, and then for epoch 2 and 4 and 8 and stuff like that. So we'll have a pretty nice idea of what's going on, because once we examine those images, you can see that the more they are actually looks like the handwritten digits from this dataset, the more we are actually doing. And this is a very simplistic way of examining the actual results. We would normally just look at the value of our loss function, which should actually go lower and lower. But we want to make things simple here, so we'll just examine them visually. So let's leave this script running for a while, and let's examine the code. So the first thing to keep in mind is that the code is actually set up so you can reproduce the results, and all of the mechanism behind that is inside conf.py. And if you're interested in creating scripts that will reproduce results every time you run it, feel free to check this out. It's useful for working with CPUs and trying to reproduce small examples. It's not really good for working with GPUs and with a lot of parallel processing pipelines. So if you're interested just with educating yourself, you can feel free to choose and use in your own scripts this conf.py model, and the only thing that you need to do is pretty much just do the import conf before you get started. And our MNIST GAN is located in just one class, and this is MNIST GAN class. And to use it, we basically just have to create a new object based on this class, and then we need to invoke or execute train method. And the first argument is the number of epochs you want to run the script for. By default we have 50, and this is again around 2 hours on GPU, a little bit more maybe. And then our batch size, so every time on every epoch how much samples do we want to actually use from our dataset before we want to actually update the internal state of our network. And you don't have to worry about understanding exactly how this all works. A lot of the times, even if you understand the details, it's a lot about trial and error. But those values works pretty well if you want to get better results. The first thing that you should consider is to just increasing the number of epochs. But this will also increase the time that you have to wait for results. Okay, but here we have, in the results folder, inside source folder, you'll see results. So you can set it up for some high number and just look at the results and stop the script once you see that the results are good. So that's one way of going about it. But 50 is pretty good starting point because you can see the results and still don't kind of spend a lot of time training your GAN. Okay, so I want to start with just examining the train method. This is our main starting point, and this is pretty much the most tricky part of the whole process. So in train method, what we are doing here is that we have to, for each epoch and for each batch we want to train our discriminator. And to remind you, discriminator is this network that will pretty much judge if the data is fake or not, if it belongs to a data set that we know about, or is it generated by a generator, right? So our first task is to train our discriminator, and here we are training it with both fake data that's coming from generator and also from the actual data that is valid. And we tell discriminator about those two data sets, and we want to make sure that everything is valid. In case of discriminator, we just train in this network as we would do with any other network pretty much. So let's look at our train discriminator part. So the first thing that we do is that we want to generate two sets of data for discriminator on each batch count. And we want to create this fake data so discriminator will know how does the fake data looks like. So we are pretty much doing it just by using the generator, the current state of generator. So we run predict on a generator, and as an input we just give it a noise. This is just random numbers here, right? Okay, so generator as an output will have a noise, and as an output it will have some kind of fake image, right? And then we basically and this is our generate images or fake image from generator. Okay, the next set of data is just the sample of the data from MNIST. So this is the next step, getting this data from MNIST. Then we are putting it all together, and this fake data and real data into one vector, in one list. And then we have to create another list or another vector that will tell which part of the data is real and which is fake. And in our case, we label fake data as 0, 0 value and real data as 1, 0. So we can start by just creating this long vector for all of the data which will have all zeros, right? But then we have to correct, because keep in mind that once we were creating this vector, the first batch size and number of samples is the real data. So we want to make sure that we label data correctly. Batch size values, those are all real data. And the second, we'll leave it at 0 because this is generated data or fake data from the generator. Okay, so I hope that wasn't too complex. And once we've done it, once we've prepared this pretty much a batch of data with fake and real data, one from generator and one from MNIST dataset, we can then train our discriminator using those datasets. And yeah, so this is how we train our discriminator on each batch count. Then the next step is to actually, once we've train our generator, so our discriminator, so it can distinguish between fake or real data and the actual correct data, then it's time to train our generator. All right, and this is how we do that. Let's go to train generator. Where is it? Okay, so here our task is slightly different because we want to generate noise. Okay, because this is how we train our generator. This is what we put into the generator. Always put noise there. And we also want to say, look, but this noise is actually real data, right? So this is the crucial moment, the very important distinction, right? So we have just noisy data and it's labeled as true. Okay, and then what we are doing is that we are training the whole network, which is the generator, also discriminator, and in our case this is all inside self.gan variable. We train this whole network using this dataset. But here's the trick. We want to make sure that discriminator won't actually be trained at this point, right? Because now discriminator will only give the feedback to generator because we've trained it before. We trained discriminator just before, so we want to just make it freeze. We want to freeze it. And we can do that using discriminator trainable false. Okay? So this is how we actually do that in those two stages. And in a moment I will show you those two networks, this generator and also the discriminator, and how they actually are mixed together, right? But the main idea behind that is that we are training both of them in two stages, right? So that's why we have train discriminator and train generator, and this is very important distinction. So those are two the most important ideas behind training those GANs and actually building them as well. And let's just, after this, let's just look at the initialization point. Let's just look at the init part of our class. And this is where all the parameters actually are existing. Here we're creating those two networks, both generator and discriminator, and also we mix them together, right? And we're also preparing data here for training our networks. And we're starting with just setting up how much noise they want to accept in generate, and by default are using just 100, which is a just length of the input that we get from generator, and it presents a pretty good results. Then we have to specify optimizer that we'll use to train both generator and also the whole network, right? And we are using just one optimizer with very specific parameters, and it works pretty well. Then we are loading our MNIST dataset, and remember this is the same way that we've done in previous section. We are using MNIST dataset from Keras, and we just run it, we're just loading it using load_data. Then the next step is to actually create this value of the vector that we'll be using first for as an output size of a generator and also input size for discriminator. We'll see how it works in a moment. This is basically just our MNIST datasets. It's 28 by 28. Those are images of size 28 by 28. So we want to create just big enough vector to feed this data. Then the next step is that we want to optimize or normalize our dataset, our values in our dataset. So we'll have it in a nice range of -1 to 1. And we want to also change the default shape of the data so it can fit into our discriminator. So we're doing all this setup so we don't have to repeat it later on. And the last step is to create generator, discriminator, and also our whole network. So when you look at our generator, so this is the actual network that we are using to generating our digits, right? And this is the one that it actually gets trained based on the feedback from discriminator. And this is pretty simple architecture, and usually you will see convolutional neural networks in generator, but since we are using just CPU, we've chosen different kind of architecture, so we can actually train something that works in a short amount of time. And one of the things that we have to keep in mind is the input value. This is our random dim. This is 100. This is the length of data that we accept. This is amount of noise that we accept inside our network, and that will be used to generate our images, right? So 100 works pretty well. The other thing is at the output, we want to make sure that we have the correct output. The length from the last dense layer, it has to match the input of the discriminator, right? So since we actually connecting those two networks, they have to match. The output of the generator has to match the input of the generator. And this is the value that I've just was talking about. This is IVS, and this is our 20 by 20, and 20 by 20, 28 multiplied by 28 vector. Okay, so this is what you have to keep in mind, right? What else? Our generator actually generates images, and that's why we have to choose the binary cross entropy to do that, to actually generate from the noise to generate those fake images. So we have to choose the right loss function here. And notice that we are using optimizer that we've defined in init function. Same goes for discriminator. We still are using binary cross entropy, but the discriminators is actually different function because it will tell if the image is fake or not. So here we are using in dense, the last layer is actually dense, single connected dense layer with just single neuron and sigmoid activation function, and this will give us just the probability that that the input image is actually fake or not. And this is different than in generator, because in generator we are generating image. So the dense layer, it actually has this, it's a 28 multiplied by 28 size vector, our image. Activation function is tan h, right? So this is the difference. In generator we generating the actual images, and in discriminator we are just checking if we just get the probability if our image is actually fake or not, right? So we'll get something from 0% to 100% probability of image being fake or not, or it being actually real. Okay, and the last method that is very important is actually when you're connecting those two layers. And by default, we want to make sure that the discriminator is actually, we freeze discriminator. We don't want it to, at the beginning, to train, right? Because we want to only generator to be trained at the beginning. And we are putting those two together, those two networks together, first by defining the actual input for our generator. So our first network in this whole GAN network is actually generated with specific input. Our specific input is actually this vector of size 100. Okay, so we accepting noise there. And then we have output. Output is our discriminator that has the generator as an input. And then we are putting it together just by creating a new model with inputs and outputs. And our model, it has, again, we are using binary cross entropy, and optimizer is all the same for all of the networks. We have a few more methods here, but those are the most important ones. Yeah, and I hope that was clear enough, and you can actually get your head around and mind around how it all works. And let's have a look at our running script. We have 6 epochs and we're still running, so let's have a look at what we've created so far using this script. Let me just open results folder. So this is our results from epoch number 1, and it's all blurry. It's not really, and there's no real distinction between that. And then it's getting better with epoch number 2. You can see that the first stage, it's usually that the noise disappears and we can see some of the results. And then we've got slowly a little bit better. So we're actually generating those results in a real time. So we've got some more from epoch 6. So this is how it works in practice. We'll stop now the script, but I highly encourage you to run it for more than just a few epochs to see the results. So I hope that this video was useful. In the next video we'll summarize this section and also discuss what you can do next to actually learn more about GANs. Until then, take care and I'll see you in the next video.